Hello, welcome to Maths with EJD. In this video, I'll be talking about the animal feed mixing problem with linear programming. Okay, now mixing problem actually belongs to a group of problems called the blending and mixing problems. Blending and mixing problems. So I'll quickly talk about this before we talk about the animal feed problem. So talking about blending and mixing problems, right? Blending and mixing problems involve creating a mixture from different raw materials. Typically, to meet specific criteria or minimize costs. These types of problems are common in industries like food production, chemical engineering, construction, and agriculture, where the goal is to combine materials. The goal is to combine materials in such a way that the final product, in such a way that the final product meets certain constraints, such as nutritional content, cost, or physical properties. Okay? In mathematical terms, blending and mixing problems can often be formulated as linear programming problems. Linear programming problems. That's LP problems, where the objective is to either minimize or maximize a linear function subject to a set of linear constraints. Okay. So in this case, of course, you have some key components. So key components of blending and mixing problems. Blending and mixing problems. Right? So you have of course, you have the raw materials. You have the raw materials. These are the ingredients that will be combined. Each raw material has a certain properties such as cost, nutrient content, or other characteristics. Then you have the mixture itself, right? You have the mixture, the final product that results from combining the raw materials. That's the mixture. Then, of course, you have your objective. So whatever the objective is, we are used to some objectives already. Typically, the goal is to minimize cost or maximize profits. Alternatively, it may involve minimizing waste or energy consumption. So it all depends on what exactly your goal is. Then you have the number four, you have the constraints. You have the constraints. So these are the requirements that the final mixture must satisfy. So examples include constraints on nutrient content, weight, or volume. Okay. So that's about the blending and mixing problems under which the animal feed mixing problem uh, uh, falls. So we want to do that using linear programming because it can actually come as a linear programming problem. So let's go for that. So an animal feed, uh, so let me just say animal feed mixing problem. Of course, since it's animal feed, right? There's a way you should combine everything so that you get the particular result you want. So I'll just go straight and talk about this. So assume, assume we have the following ingredients. We have the following ingredients for an animal feed. For an animal feed. Okay. One, we have corn, which with 9% protein, 9% protein, 3% fat, and 2% fiber. Okay. That's corn now. Then we have soybean meal. So with 40% protein, 40% protein, 20% fat, and there is 10% fiber. Okay. And lastly, we have wheat, which is which has 12% protein, 2% fat, and 6% fiber. Okay. Um, so we have the following nutritional requirements. The following nutritional requirements. Nutritional. Okay. So we need minimum. We need minimum 15% protein for the whole feed. Then we need minimum 10% fat, minimum 10% fat. Then we need maximum, maximum 8% fiber. Then, so in that case now, let's imagine that So decide, let's take the decision variables. So let those be um the decision variables. You have, let's say we have X, which is amount of corn. X is amount of corn. X is the amount of corn, amount of corn. Y is the amount of soybean meal, amount of soybean meal. And Z is the amount of wheat, amount of wheat. Okay. So that will lead us to the formulation, problem formulation. Or should that be the problem? Okay, so I mean that would just lead us to what we need to do, right? So now we want to minimize the costs. The objective is to minimize costs. So we have minimize. Z equals amount of corn, right? Together with, of course, we know we need see there. I'm trying to see 0.25x1, 0.5x1. So we need to minimize costs. Okay. Minimize the cost. So let's talk about the object. I want to be clear about the objective function. The objective function. Um, so we have the amount of corn X, Y, Z. Okay. Before I come here, right? We need to talk about this. So talking about the amount of corn, like I earlier stated. So what we have is that so for the amount of corn, imagine that corn costs, okay, let's do it like this. Amount of corn in kilogram, amount of this in kilogram, amount of this in kilogram. So let's say the corn costs $0.25 per kilogram. Okay. Then soybean meal costs $0.50 per kilogram. And of course, wheat costs $0.40 per kilogram. Okay. So in that case, we can formulate the objective function as this. It means, I mean, we can formulate the whole problem to say we want to minimize, 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 that's a lot. Minimize the cost, which is Z equals 0.25x. That's 0.5 per kilogram. X is the amount of corn in kilograms, right? So 0.5x plus 0.50y plus 0.40z, based on the cost per kilogram in each case. And all of that will be subject to all the constraints we've had before. So that will be subject to those constraints based on what we already have. So we have protein requirement. Protein requirement is a minimum of 15%, of protein, right? So in that case, minimum means it's greater than or equal to 15. But we know that for corn, if you look at corn, right, corn is 9% protein, okay? Then this is 3% fat, all right? And this is 2% fiber. So in that case, if we're talking about protein, so we have to go down the line. That's 9% protein, 40%, 9% protein, 40% protein for soybean. That's 9% protein from corn, 40% protein from soy meal, and 12% protein from wheat. So that's how we are going to go across that. So for the protein requirement now, like we said, we need minimum of 15% protein, right? So that means that we are going to have 0.09 0.09x plus 0.40y plus 0.12z, and that is greater than or equal to 15% protein. Of course, 15% should be 0.15. 0.15, that's the percentage of protein that is required. Okay, so this is the protein requirement. Protein requirements now. This is it right here. And then this, of course, is the objective function. Objective function. We want to minimize costs. Is the objective function. Then we also have another one. We have the fat requirement. The fat requirement is 10%. Okay. Fat requirement is 10%. And we know that across corn is 3% fat, soybean 20%, and then wheat is 2%. So in that case, we're going to have the fat requirement would also be a constraint. The fat requirement, like that, the fat requirement, that would be 0.03, 0.2, and 0.02. Okay, so 0.03x plus 0.20y plus 0.02z, and that is greater than or equal to 10%. 10% is actually 0.10. That's 10%. And of course, we have fiber limits. Fiber has a limit, or we can also say fiber requirements. So we have the fiber limit. So we don't want to have more than 8% fiber. So in that case, we have, and for fiber, right, in each of the ingredients, we have 2% fiber, 10% fiber, 6%. So that's 0.02, 0.10, and 0.06 for fiber. Okay. So that means we have 0.02x plus 0.10y plus 0.06z, and that has to be less than or equal to 8%. 8% is 0.08. All right. And that's what we have. Of course, we need to also talk about the other constraints, right? We have the non-negativity constraints. Non-negativity constraints. So for non-negativity constraints, that means we have X, Y, okay, all black, right? So we have X, Y, and Z. They are all greater than or equal to 0 for the non-negativity constraints. And if that is the case, then we have the problem done, problem already formulated. So now we just need to solve. And of course, you already know you can solve using um simplex method. You can solve using Python code. Of course, there are other methods like using Excel solver and all the rest of that. But then I've been using Python code. So I'll just go ahead and display how to use Python code to solve this. So look at that here. We have an animal feed mixing problem. And, we have all the objective function and all this. So if you look at this now, this is 15% and everything. So normally this should actually be 0.15, like I have over there, and this is 0.10, and this is 0.08. And you see that the transformation has been done because of the first one is actually supposed to be greater than or equal to. So when you transform it becomes like this. You have 0.15, then you have minus 0.10, and this is actually, so this is already less than or equal to problem, so we don't have to transform that. So it is just 0.08 normally, and that's what we have. So if we run that, we get, okay, so here it just tells us that the minimum cost, okay, I guess for the percentage thing, right? The minimum cost is $0.25. I believe that won't represent well. So in that case, it looks like we have to leave the percentage in the whole form. Okay. So all these that I did here, because I mean that cost is not making sense, right? To make it make sense, we have to leave it as 15, 10, and 8, just the way it is. So this will be 15, 10, and 8, exactly the way it is. And then we now have to go back to the code and leave it the way it was. Yeah, that's the only way it can make sense. So yeah, so all this. So if we run this now, then yeah, then it makes sense that okay, X, Y, Z, so 050, $25. 050, 050, $25. So using, okay, yeah, that is lean prog, I believe. That is lean prog. So what if we use pulp? So if we use pulp, it gives exactly the same result. So I mean, pulp has its own way of, so in pulp we write the problem just exactly the way it is. So makes it look like pulp is a bit better than lean prog. Okay, so 050, and then $25. That's the result. So using Python code, and by that we mean lean prog, or better still, scipy dot optimize. Okay, let me expand that. Scipy dot optimize dot lean prog, and or I mean you don't have to use the two. I just like to use the two to compare notes. So using scipy dot optimize dot lean prog or pulp, we get uh you know the amount of corn in kg, right? So X, which is amount of corn. So in this case, we get 0 kg. Then Y, we get amount of soybean meal, right? That is, we get that to be 50 kg. Okay, that's 50 kg. And then Z is the amount of what's that thing now? Amount of wheat. Yeah, amount of wheat, amount of wheat, and that is 0 kg also. If you want to really minimize cost, so it means we should just concentrate on soybean meal. Um, So soybean meal can give us everything we need. So, and because you're focusing on soybean meal, that is like 0.50 times 50. So that's 50 times, I mean 0. Half of 50. That's why that oh okay. I think there's a conflict there. Okay. What do we do now? Okay. Uh there's a conflict in the values of Z, right? So let me just make this Z star. Let's make that the objective function. Let's make it Z star. So Z star now is um $25. So the minimum cost you can have is $25, and that will mean 50 kg of soybean meal, no kg, I mean 0 kg of corn and 0 kg of wheat. Because so it looks like soybean meal is good enough to meet all the conditions that you have set. You can actually set other condition if you want everything to be involved, right? Maybe you must have a particular kg of corn and all that. So you can have something like X is greater than or equal to, or X is equal to, maybe if you want it to make sure that there's at least 10 kg of each. So you have to set that constraint that, oh, X is equal to 10, or greater than or equal to 10, or Z is greater than or equal to 10. So if you want to make sure that each particular kind of ingredient is involved in the mixing, then you have to specify that as part of the constraint. But here we don't care. So in that case, it means that soybean is good enough to meet all the needs to minimize our cost. So um so this it means that um the minimum cost of $25 is attained by buying just 50 kg of soybean meal, which meets which okay, let me say it meets all the requirements. Okay, it meets all the requirements. So that's it. So soybean meal does the job, and we are good to go. So if you have not subscribed to this channel, be sure to do that right now. Don't forget to hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment. Let me know if you wanted to teach a topic or solve a problem, and like and share so that more people can have access to this great learning. And that's been that about the blending and mixing. About, of course, on that blending and mixing problem, we have done you know animal feed mixing problem. So in the next video, I'll be talking about crude oil blending problem. So which follows the same kind of pattern. So they both belong to the blending and mixing problems under linear programming. So watch out for that and enjoy. Till I come your way again, keep optimizing. Bye.